Probability plays a role in all statistical inference. Before we dive into this idea, let's investigate a real court case. In the case that's outlined below, the prosecution used an argument based on probability, statistical inference, as well as an argument based only on data analysis, not statistical inference. The example asks, how can a prosecutor use data to detect cheating? The details of this case appear in Chance magazine in 1991. The case looks like this. During an exam at a university in Florida in 1984, the proctor, the person giving the exam, suspected that one student, whom we will call student C, was copying answers from another student, whom we will call student A. The proctor accused student C of cheating, and the case went to the university's Supreme Court. And the evidence provided by the proctor is that at trial, the prosecution introduced evidence based on data. Here is the evidence. On the 16 questions missed by both student A and student C, 13 of the wrong answers were the same. And the argument by the prosecution was that we're using data to draw an inference based on probability. He asked the question, could 13 of the 16 that they both got wrong match by chance? So if I guess he's trying to say, if they both got these same ones wrong, what are the chances that they got the same wrong answers for all 13 of those problems, you know? If you're wrong, usually your answer's kind of off because you made a mistake. What are the chances they both made the same mistake in their thinking? He argued that a match of 13 out of 16 was very unlikely with random guessing. Therefore, there had to be another explanation besides chance, and the prosecutor said the explanation was cheating. Based on this evidence, student C was found guilty of academic dishonesty, which is another way of saying cheating. So for me, I feel like it probably depends, is this a multiple choice test or a fill in the blank test? If it's multiple choice, I'd say the chances of them both having the same answers is a lot higher than if it was a fill in the blank test, but oh well, they didn't tell us that. Let's see, what else do we got? The role of random chance, using simulation to produce probability distributions. To decide if we agree with this argument, we need to determine if it would be unusual to get 13 matches on 16 questions by chance alone, if the student were to just guess. Okay, so it looks like it is multiple choice. Let's assume that each question had 4 options, A, B, C, or D. We use a computer program to randomly assign answers to each question, which mimics what happens when someone randomly guesses. Using software to imitate chance behavior is called simulation. The table below lists 16 questions missed by both students and shows how each student answers the 16 questions. Answers with a check mark show the 13 questions for which student C's wrong answers match student A's wrong answers. The computer simulation generated the last 3 columns. Each of these columns shows randomly chosen answers for the 16 questions. Matches to student A indicate with a check mark. All right, let's look at this here. I'm going to move this down. Oops. Okay, let's look at this table. So 16 questions missed by both students. Okay. Student A's wrong answer. So this computer program has just chosen 16 random selections for these wrong answers based on, four choices. And student C's wrong answers, let's say they have 13 of the 16 correct. Okay. Now let's say random answers. Now, well, they designed it so that student A and student C's, these answers would have 13 of the same, and of course, 3 wrong, 3 not the same because there were 16. 13 were the same of the 16, 3 were not the same. And then they chose randomly. Let's just choose randomly 16 times. We'll choose a letter from A to D, A, B, C, or D for the first one, A, B, C, or D for the second one, on and on and on. A check mark for those that match. In this first random answer column, there are only 1, 2, 3, 4, 5, 6 that match. So we have 6 that match there. And this is very random. Okay, and then our second try, the computer simulated it. It chose randomly A, B, C, or D for the first question, A, B, C, or D for the second question, is randomly on and on and on. This time there are only 3 matches to student A's. 3 matches. So it's not looking good for thinking, well, maybe 13 out of the 16 could have been random. The third time, the computer randomly chose A, B, C, or D for these 16 problems. 1, 2, 3, 4, 5 of them matched. Okay, and I imagine the more the times you do this you're probably getting numbers that are very close to the 6, 3, 5, maybe 4, maybe 7, but probably around there. 13 is probably not super easy to find. Maybe once in, who knows what the number is, but once in a very blue moon, you might find 13 out of the 16 match. But it's hard to imagine that that happened to be the case in this court case, I guess. So we can see that random guessing produces far fewer matches to student A. To make this more precise, let's determine the proportion of answers that match student A. For student C, 13 of the 16 matched. 13 divided by 16 is 0.8125, which is about 81%. So 81% of the time, student A and C's answers matched when they were wrong. But the set 1 that were random, 6 matched. 6 out of 16 is 38%. The second time, only 3 matched. 3 out of 16 is 19%. 38%, 19%. And then the third time, there were 5 matches, like we counted. 5 out of 16 is 31%. So those three, 39%, 19%, 31% versus the 81%, that's way different. It's not even half. Yeah, we haven't even gotten halfway there when we tried the 3 random simulations. The proportion of matches is in the randomly generated answers vary quite a bit from 0.1875 to 0.125. Oh, I think it's supposed to be, yeah. But none are close to the proportion of matches seen in student C's paper, 0.8125. Let's look at these results in a dot plot. The blue line in the proportion of matches is student C. So student C is at 0.81, which is 81%. And then these 3 dots are our random samples, or the randomly generated ABC answers. Now we repeat the simulation of random sets of answers on the 16 questions, each time determining the proportion of matches to the wrong answers in student A's paper. So just imagine if we made more and more columns on that table. On the left is the dot plot for the proportion of matches in 100 random sets of answers. Each dot represents a set of 16 answers generated by random guessing. On the right is a histogram which shows the long run pattern for the proportion of matches in 1,025 random sets of answers. So the table above, it only did it 3 times, but imagine if we did it 1,000 times. Let's look at what we got here. We got, okay, out of 100 random answer sets, we see just in this graph, a dot plot, there are lots of dots around here in the maybe 30% match area, but there are none even close to the student C's. Student C got 81% matching to student A. The closest one is this dot. It looks like it's about 60 something percent, like 62, 63%. So even after doing it 1,000 times, none were even close to the 80% or 81%. And in the histogram, you can kind of see it, the same data, but just differently. Yeah, the closest one was here. It looks like there's one bar really low there, but it's about 60 something percent, maybe 62, 63, not even close to 81%. In the histogram, we see that typical results fall between about 0.1 and 0.4, which is 10% to 40%. More specifically, if a student randomly guessed on these 16 questions, it would not be surprising to see from 2 to 6 matches with student A's wrong answers. So usually between 2 of the 16 are correct or 6 of the 16 are correct, somewhere in between. Translated into proportions, this is 2 divided by 16, which is 10%. 6 out of 16 is about 40%. What can we conclude from this simulation? Is student C unusual? Well, yes, definitely. Notice that no randomly generated set of answers comes close to the proportions that match student C's exam. And then we've done over 1,000 simulations here. Well, someone did. A proportion of 81% or 0.8125 would be very unusual if guessing. So we conclude that student C was not guessing, that it was definitely cheating. The prosecution argued that a match of 13 out of 16 wrong answers was unusual and could not be explained by random chance. Our simulation agrees with this observation. When we created answer sets by randomly guessing, we never saw more than 9 matches out of 16. That was the most, even out of 1,000 simulations, which is a proportion of 56%, well, 0.5625. We agree with the prosecution that there has to be another explanation besides chance. However, could there be another explanation besides cheating? Yes. If you don't know the answer to a question on an exam, you rarely guess at random. It is more likely that you will make an educated guess. Some wrong answers might be more logical than others. This could also explain the large proportion of matches on wrong answers between the 2 students. So this evidence is not convincing evidence that student C cheated, but we know that he did not just guess. So there was something else going on there. Okay. Let's see this argument or this example down here. A new argument based on data analysis, no use of probability. Student C appealed this case. A second trial was held. This time the prosecution made a new argument using the data. This argument did not use probability. Therefore, this argument is not an example of statistical inference anymore. The new argument was as follows. The prosecution created a new measurement. They compared every student's paper to student A's paper. For the 40 multiple choice questions on the test, they counted the number of matches to student A's paper and divided by 40. This new measurement was also a proportion. So this new argument would kind of take care of the idea that someone might say, yeah, that the students are not guessing randomly when they get an answer wrong. There's an educated guess. Some, like they said, are more logical, but for every student, they would pick logically. So if we compare student C's answers to student A's and then all the other students to student A's, that should give a good comparison. There were 88 students, and here are the results. Each dot in the dot plot above represents a student who took the exam. A dot with a proportion of 0.6 means that 60% of this student's answers match student A's answers. Notice, though, that student A is included in this data. That's why you have a 1.0, which is 100% chance. That's that one student. Of course, student A got 100% of the same answers as himself or herself. Of course, student A is the dot with a proportion of 40 out of 40, which is 1.0. This makes sense because all of student A's answers match student A. This does not mean that student A did well on the exam, though. Yeah, these dots aren't what percent they got on the exam. It's what percent they got the same as student A. We see that many of the proportions fall between 0.40, which is 16 matches out of 40, and 0.60, which is 24 matches out of 40. So it's not surprising if between 40% and 60% of a student's answers match student A's answers. Student C had 32 matches out of 40, which is a proportion of 80%. So now we're talking about just answers in general, not wrong answers. The first argument they made was just about their wrong answers. They had 13 out of 16 of the same wrong answers. Now, out of all their answers, right or wrong, 32 out of 40 matched. This does not mean that student C made 80% of the exam. It means that 80% of student C's answers match student A's answers. Student C is once again an unusual data point. Their conclusion was that this time it's harder to argue that student C is not cheating. When we compare him or her to the rest of the class, their paper had an unusually high number of matches with student A's answers, even compared to the other students. This data, together with the proctor's testimony, is fairly convincing evidence for the prosecution's claim that student C cheated by copying student A's paper. Let's see, what else? Now let's look at what's the main point. Statistical inference always involves an argument based on probability. In this court case, the prosecution used two different types of arguments to provide evidence of cheating. The first argument is an example of statistical inference because it's based on probability. We set up a simulation to reflect an assumption that the prosecutor made. The assumption is that answer sets come from random guessing. We simulated over 1,000 answers with randomly chosen answers to investigate the long-run behavior of simulated answer sets. We then compare student C to the distribution of randomly generated answer sets. Student C was unusual. We concluded that student C was not randomly guessing. The second argument is an example of data analysis with no statistical inference. The prosecutor designed a measurement and collected data from every student in this class. He compared student C's measurement to the measurement on the other students. Probability did not have a role in this analysis. Probability statements require a random event and a look at long-run behavior of random events. So this is not an example of statistical inference.